we've been talking about work and heat, right? And heat and work are both ways in which a system can exchange energy with the surroundings. And we talked about heat being quantized as Q equals mc delta T, and we can define pressure volume work as negative pressure times the change in volume. So the change in internal energy during a chemical reaction is the sum of all the heat and work, right? All the energy exchanged. And so we looked at this equation, change in internal energy is Q plus W. Well, if we set things up so there's no change in volume, so we said that work was equal to negative P delta V. What happens if delta V is 0? Then work is 0, right? And poof, it goes away and we don't have to worry about it. So then the change in energy for the reaction is equal to the heat exchanged. And they put a little subscript V there to indicate that this is at constant volume. And this is the sort of thing scientists do with math and equations, is you can find ways to simplify things and then you set it up and you do it that way. It's much better. So in a given chemical reaction, we cannot observe the temperatures of the individual chemicals, right? So instead what we do is we observe the effect on the surroundings of the reaction. And one way to do that is in a device called a bomb calorimeter. So here we have Q for the system is equal to negative Q for the surroundings. So we're making the surroundings be the calorimeter, and so Q system is also equal to negative Q for the calorimeter. Calorimetry in general is a technique used to measure heats of reaction by observing the change in temperature of the surroundings. So we have a chemical reaction is our system, and it's going to exchange heat with the surroundings. We can't observe this directly, but we can see what temperature change happens in the surroundings, and from that we can understand the amount of heat that's gained or lost by the chemical reaction. So this is a picture, an illustration of a bomb calorimeter. Nothing explodes, so that's not very fun. But this is what's called the bomb, and it's a little sealed chamber, and if the pressure changes, the volume's not going to change. And so this is where our constant volume comes in. And so this is often used for measuring heats of reaction for combustible things. Like you can put a peanut in there and burn it and find out how much energy the peanut gives off. And that could be measured in calories, which would be nutritional calories, right? And you can find out how many calories are in foods. So you've got your sample in here, and there's oxygen in this little bomb, and then we also have ignition wires so that we can start it on fire, basically. Outside the bomb is water and a thermometer and a stirring mechanism, and then this whole thing is well insulated. And so, ideally there would be no transfer of energy from this part to the outside. So the calorimeter constant is the heat capacity of the calorimeter. So specific heat is equal to the mass times the heat capacity. And so that's really useful. No, I'm sorry, I got that backwards. The heat capacity is the mass times the specific heat capacity. We usually use specific heat capacity because we're using different masses. When you're doing a reaction in a bomb calorimeter, the mass of the calorimeter is always the same, and the specific heat capacity of the calorimeter is always the same. And so we just combine them and use the heat capacity of the calorimeter. And so that's why there's no M in this equation. The M is hiding with CS in this heat capacity. So the heat for the calorimeter is the heat capacity times its change in temperature. That is equal to Q reaction, opposite in sign. And delta E for the reaction is equal to Q reaction. So here's a problem with a bomb calorimeter. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kJ per mole hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Okay, so, the first thing is read the whole problem and go back and highlight the numbers. Got all the numbers, and then we're looking for what are they asking? Well, it's not a question, it's a command. Find this in kilojoules per mole of hexane. So then let's pull out the numbers and write them down and identify them, because it's kind of hard to see them when they're all jumbled up with the words. So we've got these two temperatures, and then we've got this other guy, 5.73 kilojoules per degree Celsius. So we can kind of, think ahead a little bit. We've got a bomb calorimeter, right? And so we just learned that Q for the calorimeter is equal to the heat capacity for the calorimeter times the change in temperature. And then, let's move that out of the way. Put that there. And we also learned that the heat of reaction is equal to Q for the reaction, which is going to equal negative Q for the calorimeter, because any heat lost by the reaction is gained by the calorimeter. So these are the sorts of things we're looking for then. We've got 1.550 grams. Is that any of these variables? No. It's a mass, right? So we'll just say, well, that's the mass. Mass is this. And then we've got two temperatures here. So this should make us think about, well, delta T is the final minus initial, right? Delta T is the final temperature minus the initial temperature. So chances are good one of these is final and one is initial. So it rises from this one, that's the original initial one, to this one, that's your final temperature. So this is T initial, and this is T final. And then this guy is the heat capacity of the calorimeter. That's the C-cal right here. So we're trying to find change in heat for the reaction. So we're trying to find Q-cal then, which is C-cal times delta T. So here we've got C-cal, and we've got the information needed to calculate delta T. So it's 38.13 degrees Celsius minus 25.87 degrees Celsius. And I'm getting 12.26 degrees Celsius. If I get any of these calculations wrong, please let me know. So then Q for the calorimeter, the amount of heat, here we can assume it's absorbed because combustion, right? The temperature went up, is equal to C for the calorimeter times the change in temperature. C for the calorimeter was given to us 5.73 kilojoules per degree Celsius. times the change in temperature, 12.26 degrees Celsius. Calculator says 70.2498. And that would be kilojoules, because the degrees Celsius cancel out. We've got 3 sig figs in our heat capacity and 4 in our temperature, so that's going to have 3 sig figs. So great, we calculated qcal. So then we know that Q for the reaction is equal to negative qcal. So Q for the reaction is negative 70.2498 kilojoules. And that would be equal to delta H. Sorry, delta E. H is next. But what about those units? It wants kilojoules per mole of hexane. Yeah, so we were given the mass of hexane. So this is the amount of energy for 1.55 grams of hexane. So we could write it like this. It's that many kilojoules for 1.550 grams of hexane. Well, it wants moles. Can we convert grams to moles? Sure we can. 1.550 grams of hexane, C6H14, converting to moles, we're multiplying by moles, dividing by grams. And then we need the molar mass. So it's 6 times 12.01 plus 14 times 1.008, or 86.172. So 1.550 divided by 86.172 is 0.017987. I'm getting tired of writing numbers. How many do I need? I need 4. So I need 3 moles. So I'm going to take this and put it in there for the mass. So I'm looking at the quantity in moles, not in grams. That doesn't look like a 7. So I've got negative 70.2498 divided by 0.01798773. Negative 3905.5 kilojoules per mole of hexane. 3 sig figs. So we could say negative 3910, but better would be negative 3.91 times 10 to the third kilojoules per mole, because then there's no uncertainty about whether that 0 is significant or not. If you're converting a number from decimal to scientific notation, it's very important that you get the sign on the exponent correct, and some people are messing that up a little bit on the worksheets. So remember, we look at the original number and ask ourselves, is that a big number or a small number? 3,910. This is a big number, right? So then this should be a positive number, because if I get a big paycheck, I feel positive about it. And if I get a small paycheck, I feel very negative about that. Right? Any questions? And you just stand back and look at that, you're like, oh my goodness, that's really complicated. Well, it is, but then again, it isn't. You just have to be able to pick the pieces out and see how they go together, and that takes a lot of practice.